Well, good morning to all of you. Welcome to the free lecture series on the power electronics. Here now we are going to learn the lecture number 2.9, that is called full wave uncontrolled diode rectifier using R load. So in the full wave rectifier, we are having the two types of the categories. The first category is basically focusing on the midpoint connection and different types of the loads. And second category is basically focusing on the bridge connection having different types of the loads. So let's first move on to the first category. It's called this midpoint connection. This is first category is called midpoint connection. Midpoint connection. The circuit diagram for the midpoint connection is going to be like this fashion. This is the transformers, which is called isolation transformer, which is used to make the system safe. Otherwise, there will be a short circuit in some conditions. Like this. This is the diode 1. This is our respective R load. We are taking R load for the sake of explanation, and this is the diode 2. Like this. And the basic important thing in order to learn this, that is the convention for the polarity. Here I am saying that this is the VS supply voltage like this. This point is A, this point is O, this point we are taking as a point B, and we are assuming during the positive half cycle this is Vs and this is basically Vs. And the load side we are assuming a plus and minus like DC voltage V0, and current is entering in like this fashion. This is the assumption we have to make before starting the analyzing of it. So the load current and the load voltage is, I am assuming plus here and minus here. You can take the plus here and minus here, but for the sake of I am taking the observation. So first we can draw the basic operation. This is diode 1, this is diode 2. So during positive half cycle, this plus will tries to on this diode D1 and it going towards the load, and during the positive half cycle similarly in this part, the OB part is having a plus and minus. So this the current flowing from the source like Vs is going to be turn off diode. So during positive half cycle, we can say that D1 becomes on and we can say that D2 becomes off. And the circuit is going to be like this. This is our supply voltage. This is our transformer primary. And we can say that this is the supply. And it becomes on and the current is flowing to the load like this. Similarly, this is plus and it becomes off. So if we take this is plus, this should be Vs. The current is flowing like this and it is moved towards this load side. Plus minus Vs. If I am making the KVL equation, so we can say that minus Vs plus V0 should be equals to 0. Here we can say that the output voltage equals to the source voltage when diode D1 becomes on. This is plus minus Vs. This is the polarity of the D2. So we can say that this is plus minus V1. This is plus minus V. So here, if I closely examine this kind of the wave circuit during the positive half cycle, this plus Vs turns on the diode D1 and current is flowing through the load and energy is dissipated in the resistance. Similarly, if I taking the OB part, then we can say that the current is flowing like this, but it turn off diode because these are having the cathode is there. So this becomes off, this becomes on due to the positive supply, and we are just observing the circuit. Then we can came to a conclusion that V0 is equal to the source voltage, and here if I just making a loop in this equation, then we say that minus Vs minus V0 minus VD2 should be equals to 0, and we can say that VD2 should be equals to minus of Vs plus V0 Here we are obtaining Vd V0 equals to Vs, so it should be minus 2Vs, or we can say that like this. So the peak inverse voltage, this is called the peak inverse rating. Peak inverse means when diode becomes on, the voltage across the device is called the peak inverse voltage. Basically, the device rating, the selection of device rating basically depends upon the peak inverse voltage, and in this case, the diode V2, the diode D2 is having a feeling a voltage of minus 2 Vs across it when it becomes off. Now come to the waveform, then we can analyze it. The basic waveform like this. Now this will be taken as a omega t axis like this. If I am taking this is the supply voltage, if I am taking this is the output voltage, here I am taking the output current, here I am taking the voltage across diode D1, and the one thing which is remaining, right, want to complete it, is basically you can see that this is another waveform, and here we are taking the voltage across the diode V2. So supply voltage is basically positive, then it is negative, then it is positive, and it is negative because supply voltage plus the minus plus the plus. And during the positive half cycle, we are obtaining an output voltage of V0 equals to Vs. So during the positive half cycle, we are obtaining the output voltage of V0 equals to Vs, and during the positive half cycle, we can obtain the expression of current, basically like down the circuit, it should be I0 equals to V0 divided by R. So the magnitude of the current is going to be decreased because this resistance comes into the picture. So the expression, the waveform same, it is going to be like this. This is V0 divided by R. Here the diode VD1 becomes on, so it should be short circuit, and when it comes to the diode V2, it will experience a maximum minus 2 Vm. It should be minus 2 Vm of peak magnitude should be observing by this diode V2. This is the actual waveform that we are obtaining during the positive half cycle. Now come to the negative half cycle. In the negative half cycle, we can say that the circuit is going to be like this fashion. This is basically supply voltage is plus and minus. This is the full wave rectifier like this. This should be the transformer. This is the midpoint connection. This is transformer, and the load is connected going to like this. So supply is negative means this is plus, this is minus, this is plus, this is minus. This voltage is Vs. This voltage is Vs. We are observing Vs, and due to the supply is negative, the current is flowing like this, and it will turn off the diode D1 like this. So we can say that it is turned off and having a the voltage of V1. Similarly, during the negative half cycle, the diode D2 becomes on, and the current is going to be flow like this. It should be like this. So we are, and the polarity across the load we are observing like V1. This is I. So we can say that the diode D2 becomes on and D1 becomes off automatically due to supply. In apply KVL, if I apply KVL equation, then we can say that the minus Vs plus Vs minus V0 equals to 0. Here V0 equals to Vs. Output voltage, still we are getting the output voltage positive across the load when supply is negative. And if I just making the expression of current, it should be equals to V naught divided by R. It should be Vs divided by R. So this is the expression of the current. And the second thing, the voltage across the diode D1 is going to be taken by making a loop like this. So plus, making a different color, should be plus Vs plus Vd1 plus V0 should be equals to 0. And we can say that the output equals to minus 2Vs like the previous case. So when it comes to the waveform, when supply becomes negative, output voltage is equal to the source voltage, which is positive, and output current is equal to the Vs divided by R, this should be the positive. And we can say that we are observing that the Vd1, this is Vd1. The Vd1 is basically having a negative peak of minus 2 Vm, and after that it becomes again on. So if I complete the waveform like this, the Vd2 will basically shorted because of the negative supply, and this is the waveform that we are obtaining. And during the half cycle, again the negative half cycle, there will be a positive cycle. The same waveform is going to be repeated like this fashion. We are obtaining this. Like this. It should be minus. So supply voltage is AC. We are obtaining the DC waveform like this fashion. This is called the full wave rectifier using a midpoint connection for the R load like this fashion. So I think you will understand this. Now come to the average output voltage. If I taking the magnitude like this fashion, this is 0, this is pi, this is 2 pi, like this and so on. So we can say this is the output voltage. It should be 0, it is pi, it is 2 pi. So time period is basically the repetition of cycle, that is called, this is called time period. So V0 equals to 1 upon T, 0 to T, Vm sin omega T, d omega T. V0 equals to 1 upon pi, 0 to pi, Vm sin omega T, d omega T. You can say that V0 equals to Vm upon pi, integration of sin omega T, it is equals to the cos omega T. It should be 0. If I solving this, V0 equals to Vm upon pi, taking the negative sign inside the bracket, so it should be cos 0 minus cos pi. V0 equals to 2 Vm upon pi. This is the expression of the output voltage, the average output voltage for the full wave rectifier using R. Now, take the expression of the RMS output voltage. It should be V0 equals to 1 upon pi, 0 to pi, Vm sin omega T whole square d omega T. Not equals to Vm upon root pi, integration of 1 minus cos 2 omega T upon T d omega T. It should be V0 equals to Vm upon root pi, integration of the level plus 0 to integration of 2 I minus 0 minus sin omega T divided by 4 sin pi, sin n pi, sin 2 pi, sin 3 pi, all the sin components are 0 and sin 0. So the resultant output that we are getting is going to be like this. V0 equals to Vm or root pi multiplied by root pi divided by root 2. Root pi is cancelled out. So we can say that VRMS equals to V upon root 2. In a full wave converter, we are obtaining Vrms equals to Vm upon root 2. So this is the expression of the output voltage for average output voltage and the RMS output voltage. Now the average current, is basically I naught equals to V naught divided by R. So it should be 2 Vm upon I. And similarly, we can check the RMS current. V I RMS equals to V RMS